Hello students, welcome to Bachelor of Science, subject Chemistry, Semester 3, paper code CHC 103, paper title Physical Chemistry. I am Ms. Fatima Fernandez, who will be teaching you Physical Chemistry for this particular semester. Today we are going to start with a topic, conductance. Now, what is the syllabus under this particular topic? So we have conductivity, equivalent and molar conductivity, a variation of this conductivity with dilution for weak and strong electrolytes. We have Kulrauch's law of independent migration of ions, ionic mobility and factors affecting ionic mobility, transference number and its experimental determination using moving boundary methods, application of conductance measurements, that is solubility and solubility products of sparingly soluble salts, ionic product of water, and conductometric titrations. It's a 5-hour topic, so we have to complete this more or less in 5 hours, that is 5 lectures. What is conductance? The substance or substances that allow the passage of electricity to them are usually called as conductors. When current passes to any substance, those substances are called as conductors, while those which do not allow the electricity to pass through them are called as insulators. Usually, if we take a wire, we see that it is usually plastic coated or rubber coated, so that we don't get a shock. Current should not pass through us, so there is a rubber or a plastic coating for the wire. The wire which runs inside is usually of copper and it is a conductor, whereas the coating is an insulator. That is just an example. Now, when we talk about conductance here in chemistry, we talk about electrolytes first. An electrolyte is a compound that ionizes when dissolved in suitable solvents such as water. What do we mean by ionization? Ionization means, suppose I have an electrolyte, say HCl. When you dissolve it in water, you will get H plus Cl minus ions. So it ionizes. What it means is it ionizes. So an electrolyte is a compound that ionizes when dissolved in suitable ionizing solvents such as water. Or an electrolyte is a compound which produces an ionic solution when dissolved in an aqueous solution. It means the same thing. This includes most soluble salts, acids and bases. For example, when sodium chloride is placed in water, the salt dissolves into its component ions. Example, here we have sodium chloride will give us sodium ions and chloride ions in an aqueous solution. So this is an example of a salt. Example of a base would be, I have sodium hydroxide, which would give me sodium ions plus OH minus ions in an aqueous solution. Electrolytes conduct electricity due to the flow of ions. Now it is these ions, when they are present in the solution, which are responsible for the conduct of electricity. Now these electrolytes are further classified into strong electrolytes and weak electrolytes. Under strong electrolytes, we have HCl, sodium hydroxide, sulfuric acid, etc. Under weak electrolytes, we have acetic acid, ammonium hydroxide, etc. What are non-electrolytes? Non-electrolytes do not conduct electricity. Electrolytes conduct electricity. Non-electrolytes do not conduct electricity. They are solutions which contains solutes and solvents. Solutes and solvents. Those compounds which produce large number of ions in a solution are called as strong electrolytes. I had given you the example of HCl, sodium hydroxide, KOH, etc. So those compounds which produce large number of ions. Why they produce large number of ions? Because whatever whatever this HCl, when you dissolve it in water, it will give you H plus Cl minus ions. In other words, this HCl what is taken completely dissociates. That is why it produces large number of ions. Whereas in weak electrolytes like acetic acid, we have CH3, COOH will give you very few CH3, COO minus ions, acetate ions, and a few H plus ions. So weak acids, weak bases do not dissociate much. More of it will remain as acetic acid. It will not produce much ions. There is only partial dissociation of weak electrolytes, whereas strong electrolytes are completely dissociated. So you have to remember this point. Strong electrolytes, there is complete dissociation, and that is why there is large number of ions, whereas for weak electrolytes there is partial dissociation and hence small number of ions. Again, the same examples. We have strong electrolytes, all these examples. We have weak electrolytes, and we want to stress on the non-electrolytes here. Non-electrolytes, we have urea, glucose, sucrose, etc. So when you dissolve it in water, it will remain as urea and as water, that is solute and the solvent. Our solute will be urea and our solvent will be water. So when you dissolve urea in water, urea does not dissociate to give us ions. Okay, so such type of compounds are called as non-electrolytes. Many times we talk about a replacement electrolytes. If you have heard about the sportsmen's, one relevant example here, which we do in our day-to-day life. We talk about electrolyte solution in sports drinks. In sports drinks, you remember, or you must have seen on the TV, or you must have seen in your real life, this sports people, they drink something every now and then, that is nothing but a replacement electrolyte. That is, they lose lot of sweat when they exercise, when they play. They, all human beings, they will sweat, and they lose a lot of water, lot of sweat, and lot of ions along with that. Okay, there are a lot of ions in our body, so these ions are lost in that process, and as a result, to replenish, it is very necessary that we replenish them, the ions from the body. How do we replenish? By consuming more of these ions. So when we consume, when we drink this sports drink, you know, or, or sometimes when we are sick, we have vomiting or diarrhea, we are advised to take ORS. ORS is uh, electrolytic solution. It's a replacement electrolyte. So you have to dissolve it in water and drink. So the ions from our body are replenished. Now in metals, it is usually the electrons which are responsible, which allow the metal to conduct electric current, whereas in electrolytes, it is the ions. So in metals, it is the electrons, whereas in electrolytes, it is the ions which carry an electric charge. Now what is conductance? Conductance is the ease with which electric current flows to a substance. By now we know that when we take an electrolyte, there are ions produced when it is dissolved in water. And suppose an electric field is applied, these ions will move. So when they move, they carry with them some amount of current. So conductance is the ease with which this electric current flows or is carried by this particular ions. Now conductance, we know, is inversely related to resistance. Conductance and resistance are reciprocal of each other. Here we have conductance is 1 upon R, or we can write resistance is 1 upon conductance. So they are reciprocals of each other. Resistance is given in ohms. So what will be the unit of conductance? If unit of resistance is ohm, then the unit of conductance will be ohm inverse. The unit of conductance will be ohm inverse because it is the reciprocal of resistance. The conductance of the unit of conductance is also Siemens. It's the SI unit of conductance. Also, we make use of another unit in our laboratory. What we make use of when we do our practicals, we make use of this particular unit. Okay, so we write the conductance in moles. So the units of conductance, this is Siemens. Usually it is the SI unit. It is written as capital S, and in terms of resistance, I told you the unit of resistance is ohm. So the unit of conductance will become ohm inverse. So you can either write the conductance in moles when we do practicals, and most of the time in our textbooks we have specific conductance, so they make use of this particular unit. Ohm inverse is used, and Siemens is used as a SI unit, and the symbol used is S. This is how we find out the conductance. We take a cell and we dip it in the solution. So this is our electrolyte solution, which will contain the ion. So I'll write here, it is a electrolyte. So electrolyte will give us the ions, and this is the conductivity cell. This is the conductivity cell, and this is usually connected to our instrument. So we have a conductometer. Okay, so it will give you the readings directly on this. So this is our conductivity meter. Okay, so this is how we find out the conductance. We dip the cell in the solution. Okay, this is an electrolytic solution which contains the ions, and depending upon how many ions are present in this solution, you will get your conductance value. Higher the number of ions, higher will be the conductance value. Now, what is resistance? All this time we said resistance is the reciprocal of conductance and conductance is the reciprocal of resistance. Many a times the students also say the same thing for Viva. Whenever I ask them what is conductance, they say it is the reciprocal of resistance. And then what is resistance? Then it is the reciprocal of conductance. This is not what is expected. The tendency of a material to stop the flow, to resist the flow. The term comes from resistance, comes from resist. It resists, it stops the flow of current in is known as resistance. Okay, the tendency of the material to, it does not allow the flow of current. So some materials are like that. So they resist the flow of current. And as I've said already, it is measured in ohms. Symbol you all know, ohms. Now, here resistance R is said to be proportional to the distance L between the electrodes and is inversely proportional to the cross-sectional area of the electrode A. Now what is this L and A? Just now we have shown you the cell, isn't it, which is dipped into the solution. So there inside you have two electrodes, two plates, two platinum plates. Let me draw all of this. So this platinum plates have to be dipped into the solution. So you have, say, a beaker, and these plates have to be dipped. Your water level should be above these two plates. Your solution level should be above these two plates. This is then connected to our instrument. Okay. Now, what is this L and what is this A? L is the distance. So if I say these are the two plates, this is one plate, this is another plate, they are not equal. Okay. Okay. Which are present inside the this is your cell. So the L is nothing but the distance between these two electrodes. This is L, and A is the cross-sectional area of these two platinum plates. A is the area of cross-section. So, L upon A, you will learn that in the next two slides. L upon A is called as a cell constant. It is a constant for this particular cell. So, it is called as cell constant. Now, the length between this two plates and the area of cross section of these two electrodes will always remain constant inside the cell here. So what happens for this particular cell, this value L upon A is always a constant. So it is called as a cell constant. Now here we have said resistance is proportional to, so let me write here, resistance is proportional to the distance L between the electrodes and inversely proportional to the area of cross section of the electrodes. So this is our equation. Resistance is proportional to L upon A. Now I remove this proportionality sign and I introduce a constant. So if I want to put an equal to sign here, in other words, I have to introduce a constant. So when I put an equal to sign, I have to introduce a constant. This constant is the proportionality constant, which is called as specific resistance. This is called as specific resistance or resistivity. It is a rho. It is called as a rho. The symbol is rho and it is called as specific resistance or resistivity, and it is a proportionality constant. That is, it is introduced because we remove this proportionality sign. This is a very excuse me, it's a very important equation. Okay, we number it as equation number 1. So here, this is exactly what I have explained. Cell constant is equal to L upon A, and it is a constant for a given cell. The value of this cell constant of this cell will not be the same as that of another cell. Each cell will have its own cell constant. Now we know what is conductance, we know what is resistance, we know what is resistivity or specific resistance. Now let us see what is specific conductance. Now, as we have said, resistance is the reciprocal of conductance. If resistance is the reciprocal of conductance, then specific resistance is the reciprocal of specific conductance. If resistance is inversely proportional to conductance, then specific resistance is inversely proportional to specific conductance. This is specific resistance, this is specific conductance. This is resistance, this is conductance. They are inversely proportional. So if this is inversely proportional, then specific resistance and specific conductance are inversely proportional. So K is the specific resistance. Okay, the symbol K is used for specific conductance. Now, using equation 1, what was our equation 1? Equation 1 was, do you remember girls? Resistance is equal to L upon A into rho. We can write rho here also. It is rho into L upon A. So in place of resistance, it is 1 upon conductance, and in place of specific resistance, we have 1 upon K, which is the K is the specific conductance, and L upon A is as it is. Okay. Now, let me rearrange this equation. If I rearrange this equation, I take this K on the other side. So from the denominator, it will go in the numerator. If I take it on the other side, and K, which is there in the, C, which is there in the denominator here, will go in this particular numerator. And your equation will become K is equal to C into L upon A. So if you want to find out specific conductance, then we have to make use of this particular equation. Okay, so this is another very important equation. I don't know, you can number this as equation 2. Now, if I put L is equal to 1, that here L is equal to 1 centimeter and area as 1 square centimeter, what will happen to this equation 2? Equation 2 will then become K is equal to C. L is 1 and A is 1. So in place of L, I'm going to put 1, and in place of A, I'm going to put 1. So K is equal to C. That is, specific conductance becomes equal to the conductance when the length between the two electrodes is equal to 1 centimeter and area of cross section of the electrodes is 1 square centimeter. So that is how we define specific conductance. Specific conductance is equal to the conductance of the solution when the length between the electrode is 1 centimeter and area is 1 square centimeter. So here we have the definition. It is specific conductance of the solution is defined as the conductance of a solution of 1 centimeter length and having 1 square centimeter as the area of cross section. In other words, what we have defined is the length is 1 centimeter. Length is 1 centimeter and area of cross section is 1 centimeter square or 1 square centimeter. Then specific conductance is equal to conductance. Now, length is 1 centimeter, area is 1 centimeter square. If I take a box, is a cubic box, which means all the sides are equal to 1 centimeter. This is 1 centimeter, this is 1 centimeter, this is 1 centimeter. Okay, so it is a box, it is a cubic box. Now, if I consider this as this side as one plate of the electrode and this side here as another, the opposite sides. Okay, so if this say is positive and this is negative, these are the two plates in the cell. So if these are 1 centimeter apart, so the length between them from here to here is 1 centimeter. And what is the area of a cube? Area is length into breadth of a cube. Area of a cube, how do we write? Area of the cube is length into breadth. So length and breadth are the same. So it is 1 centimeter by 1 centimeter. So it is 1 centimeter square. So it means this is a cube. When I say length is 1 centimeter and area is 1 centimeter square, it means it is a cube. Now, specific conductance is the conductance of 1 centimeter cube of the solution. So if I put a solution here in this cube, it becomes 1 centimeter cube of the solution of the electrolyte. So whatever conductance is produced by this particular solution, which is in 1 centimeter cube, becomes equal to specific conductance. Now, what are the units of specific conductance? What are the units of specific conductance? We have the formula. So you have to remember this particular formula. Now, conductance is in moles. Okay, length is in centimeters, area is in centimeter square. So if I cancel out 1 centimeter from here and 1 centimeter, there are centimeter into centimeter. So I cancel, say, 1 centimeter. What remains is centimeter. I'll write it here for more clarification. So this is the unit of conductance, and this is the unit of length, and the unit of area will be centimeter into centimeter. When I say centimeter square, unit of area is centimeter square. It means centimeter into centimeter. So 1 centimeter from the numerator will cancel with 1 centimeter in the denominator. What will be remaining is moles centimeter inverse. So this is the unit of specific conductance. Instead of moles, you can use the SI unit. Okay, instead of moles centimeter inverse, you can use the SI unit. So in place of conductance unit, that is, we will have to use Siemens, and you have to use meter inverse. Instead of centimeter inverse, it will be meter inverse. So this is your SI unit. Suppose you are writing in terms of ohms. Okay, we have said the unit of conductance here. This is conductance. So the unit of conductance we can also write as ohm inverse. We have just studied that, and this is centimeter inverse. So the other unit is ohm inverse centimeter inverse. So till this will be our lecture number 1.